Okay, welcome everyone to the GRASP Student, Faculty, and Industry seminar. Today our speaker is Dr. Monroe Kennedy. He is an assistant professor in mechanical engineering at Stanford University. He leads the Assistive Robotics and Manipulation Laboratory, which will develop robotic assistants by focusing on combining modeling and control techniques together with machine learning tools. Together, these techniques will improve performance for tasks that are highly dynamic, require dexterity, and have considerable complexity and require human-robot collaboration. Professor Kennedy received his PhD in mechanical engineering and applied mechanics, and a master's in robotics at the University of Pennsylvania, advised by Dr. Vijay Kumar, with a focus in robotics in our very own GRASP lab. He received the GEM and NSF graduate fellowships. During his graduate studies, his research focused on increasing the abilities, effectiveness, robotic mobile manipulators performing complex service tasks in unstructured environments with considerations for working alongside human collaborators. And with that, take it away.
Thank you very much for that great introduction, and that's great to virtually be back. Today I'm going to talk to you about considerations for human-robot collaboration. So here at Stanford, I started the Assistive Robotics and Manipulation Laboratory. The mission of our lab is to develop intelligent assistive technology that improves human life. We do that by looking at robotics in these three main categories. Robotic assistants, you can think of these as sort of corporeal robots that are able to work alongside human counterparts or work for them, perform some of the service tasks. Intelligent wearables, where these augment the person in some way. And connected devices, which may be passive, but perform some service for the person, which requires situational awareness. Across all of our projects, we're really looking at this sort of problem here, where you have a robot, a human, and some complex task or environment that they need to collaborate in. To be effective, we know that a robot needs to model itself. It needs to be able to model the task. But to be an effective teammate, it also needs to model the human collaborator. And so understanding how the system works between the human, robot, and task is critical to being an effective collaborator. In my short time here, year and a half now, I've been very fortunate to attract many brilliant students. Here you see a mix of my PhD and master's students who work across many areas and many problems, and I'll cover them all later in the talk. So let's talk about the evolution towards collaborative robotics. In the 80s and 2000s, the big thing was automation. How do we make these robots capable of precisely and repeatedly doing tasks which required a high level of arrangement of our environment to be successful? Then we saw the onset of autonomy, where these vehicles would have to be precise and safe, but they would need to also operate in unstructured environments. Then we saw the case when we wanted to have many robots work together, usually in a sort of centralized scenario where there's an oracle that's telling the other agents what to do. And then we saw the need for decentralized swarms, robots that could work together in big teams, but maybe there wasn't one primary leader telling every single agent what to do, because that might not scale necessarily well, either computationally or even just due to communication constraints. And then finally, we have the onset of augmentation or collaboration with a human counterpart, where here we have a robot that is working alongside a human teammate. And so there is no digital communication. How do they work effectively together? So maybe what kind of tasks can we think of when we want to consider human-robot collaboration? What does it look like? You can imagine, for instance, having a human carry an object with a robot, where the robot is able to support part of the load and understand where the human wants to go as they carry something together. You could imagine having a wearable robot that's able to alert a person on their environment and help them with stability, or even assist with a lower limb exoskeleton. You could imagine a case where you wanted to do a macro task with a robot agent, like carry a group of boxes from one location to another. How do you describe the task to the robot? How does it effectively work with you in an efficient way? You can imagine having intelligence inside of a prosthetic, which would decrease the cognitive load on the human counterpart. You could imagine in self-driving vehicle scenarios, having a robot that understands when and how transition of control should be managed and done, and how is the most efficient way to actually present risk to the counterpart, to have this communication in this sort of switching case. And in the sort of space of connected devices, increasing the capabilities of the human to collaborate with more people, consider the translation of American Sign Language. When you want to think about sequential language, how can you endow the human with the capability to understand and translate these more complicated forms and modalities of communication? So 3 questions I want to ask today is, what makes an effective collaborator? What tools do we have, and what do we need to make robots effective collaborators? And what must be considered for human-robot teams? So starting off with what makes an effective collaborator, many of you might even know where this picture is. This is Levine 457. We have a group of quadrotors flying together here in a centralized way. And these sort of systems usually might have some sort of base station, like an oracle, that's working on these platforms, telling every robot where they need to be in order to cooperatively perform a task. Here, take the figure 8. As you scale these systems up, perhaps if you need to have this distributed computation, maybe you want these agents to reach consensus on a desired behavior, which means they all need to know their role, and they need to be able to communicate, at least with local partners, digitally to achieve that objective. But if we begin to think about biological systems, particularly humans, we're really good at communicating and coordinating even without digital communication. So what makes an effective team like this? I would argue that it consists of having shared goals and objectives among teammates, the ability to model teammates for behavior prediction, and the ability to plan given personal and teammate roles. So if we think about how this is actually achieved, we have to consider the fact that biological systems have limited communication modalities compared to robotics. And those are usually limited to audio, vision, or tactile. So in the case of audio, right, you have high specificity, but it might be slow. So if you think about speaking with another person, if you're not speaking in tandem, you have to wait for the first person to finish and then respond. And in that process, convey the concept that you're trying to convey. You also have vision, where you can observe what the other agents are doing. And that can be mutual. You can observe each other and understand really quickly what must be done. Information exchange can be very quick, as well as detailed. Not only could this work in simultaneous or operation tempo tasks, you can even describe more complex concepts. Here, we see a direct example from nature where bees are able to perform a dance, which the others observe, and this gives them information about where their goal is in terms of gathering food. And then finally, you have the space of tactile communication, right? And in this case, again, it can be very fast. If you look at how quickly the play is being communicated to the individual in the middle, this is quite incredible. However, there's a direct limitation, which is proximity. You need to be close enough to convey that tactile communication information. So if we want to break teamwork down into its most fundamental components, 2 that I think are really key to think about is 1, role understanding. So given the actions of others, the robot must ask, what is my role? And is my role unique given the task? And secondarily, we have this interagent trust, which is conditioning your behavior based on an understanding of how your neighbor or your collaborator plans to collaborate and what their goals are. And so the components of this are 1, an agreed objective, and 2, a known behavioral model. So to kind of break this down with an easy example, consider this lane changing problem where red wants to go from its right lane to the left and cut blue off. There must be agreement on the objective that both agents shouldn't collide or don't want to collide. And then blue must have the control authority to ensure that doesn't happen, either maintaining velocity or slowing down. If red knows or believes that blue shares this objective and has the control authority to achieve it, then based on those metrics for trust, red can take that lane changing action. And we can come back to this, but I will motivate this by saying this is directly related to fundamental optimization and control definitions. So what are the natural limitations of biological teams? Right, a few that you can think of are limited communication modality, limited dexterity and strength to weight ratio, as well as limited perception. And how do biological teams overcome them? They do this through understanding their role given the team and task. They model the task and they model their teammates. So moving to our second question, which is what tools do we have in robotics to make robots, effective collaborators? I'd like to touch on three main components and really thinking about sort of corporeal systems first. So the first is proprioception and control. The second is perception, sensing the environment. And the third is intelligence. How do we model and make decisions? So starting with proprioception and control, we can think about a robot, particularly manipulators, as this is my space. We have the kinematics of the system. Given my joint angles, where am I in space? And then we might have some inherent knowledge of our dynamics. If I move in a particular way, how do I expect my system to move? If I actuate in a particular way, how do I expect my system to move? We have motion planning. So a lot of these techniques, particularly as the degrees of freedom of your system increase and become more complex, kind of blend into sample-based methods. Here, an RRT method is shown to navigate from one pose to another. And in the space of control, particularly when you're interacting with, imagine a person or the environment, this could be through manipulation, or even if you're having a walking robot that's interacting with the ground, then force control is very important when you're interacting with your environment. But even more generically, this goes into understanding how your control inputs will affect the underlying dynamics of your system. Focusing a little bit as under the space of human-robot interaction, particularly this sort of force/environment interaction components. So if you're working around a human or in an environment where you need to be sensitive to have the force you're putting on the environment, usually there's a sort of trade-off between whether you want to use something called impedance control or admittance control, where in the case of impedance control, you want to mimic particular dynamics of your system. You want to have this sort of simulated mass, dampening, and springiness for when you interact with the environment. In the case of admittance control, which is usually a technique that's considered when you want to have direct interaction with a human counterpart, you're saying if there is an input, an external disturbance to my system, how can I react with an inverse of the impedance method? So how soft can I be when the environment, or the person in this case, interacts with me? For perception, right, we have camera sensing, which is a very powerful modality for sensing in general. Cameras are relatively cheap, and yet there's so much information we can pull out of them. We have active sensing techniques, which are able to send usually laser light or IR light into the environment, and those reflections give the system knowledge of the surroundings. And we have many advances in tactile sensing as well, which are very useful when you're in direct contact with your environment. So now I'm going to take a moment to talk about one of the projects that we're really trying to address in this space, because we asked ourselves the question, what's really limiting robots from being in people's homes right now? You might not be too concerned about a PR2 being able to navigate through your house without bumping things, if there's enough space. You might even be able to pretty confident that it can detect things that it should be able to do. But I would argue one of the limiting factors, at least for me, for putting a robot in my house and just leaving it and expecting it to do all of my chores while I'm at work, is the ability to successfully manipulate objects, and particularly thinking about how objects might slip out of your hand. There's information there, particularly for friction, that must be utilized in order to be successful. So this is an amazing video by OpenAI, where there are external cameras that are watching this hand manipulate this Rubik's Cube and solve this Rubik's Cube in hand. The tactile sensors aren't leveraged as much as these external cameras that are doing this. And this is, for now, the sort of holy grail for what we would like to be reliably and transferably to new objects. And so if we think about where we are, this is a version of the gel site sensor. Here, you're looking through one of the cameras and one of the fingers that's able to see the deformation causing the normal force. And as it puts the ball on the peg, the resulting friction or shear force being exerted. And this information together can give the system information about its manipulability. So if we look at the procession of these sort of tactile sensors, we have the trusty biotac sensors, which give you these normal forces in one dimension. We have the 2D vision-based sensors, particularly gel sight here shown on the digit. We have 2.5D because there's some curvature in these fingertips that are able to actually, in this case, use a picoflex time of flight sensor to observe the inside of a pneumatic gripper that's blown up to contact the environment. But due to the sensing modality, there's a limitation on size to make it a lot smaller. And then finally, we have this amazing work out of Berkeley here for OmniTac, where they actually use micro cameras to observe the surrounding of the curved fingertip to do the same manipulation, with the primary constraint being the cost of these micro cameras. So when we approached this ourselves in our lab, we thought of these 3 phases we wanted to take this through. First is the design, and we asked, can we leverage anthropomorphic inspiration in a curved fingertip capable of deforming and sensing friction? Then we wanted to move to modeling. How can we efficiently model this continuous curved fingertip at high resolution in a computationally tractable way, as opposed to like FEM, and characterize stable grasps using all of the previous work that's been developed over decades to basically characterize form closure, force closure, and the stability properties that are associated with that. And then finally, use these models in motion planning. How can we basically leverage these efficient continuous models in our fingertips to plan multi-finger grasps for in-hand manipulation? So this is a CAD design of our current sensor that's in the work. We're very close to finishing this. We're very excited about this design. The way it works is we have a fisheye lens that has an aligned center with the contact surface of the outside of our sensor. And then we're trying to approximate equal angular properties of the fisheye lens such that when you contact the surface, we can see that deformation inside of the lens with a calibration phase in between. So this is the scale factor. Here, my student Juan Kim Du is holding the sensor close to his hand there, and you'll notice that there's LEDs inside of this sensor. So the motivation for that is really allowing us to have different views of the deformed surface, and by using the shadows that are cast by the different LEDs, and therefore their different colors, we can say something about the deformation of the Lambertian surface. And so what we plan to do is have these actually iterate at a very quick rate, rotate in a very quick rate, which will allow us to get multiple perspectives of an indentation and feed those into our network for predicting deformation and then forces. And so this is an early calibration setup for our system. Since then, we've actually miniaturized this even more, and we're working on obtaining actual deformation information and force information from this surface. And our model is a generative model. We want to model the surface, model the expected normal and shear given the image data, but we want to actually have some metric for uncertainty when we do that. And that's what you see in this top figure, because obviously, there will be some uncertainty in that measurement data. If we can then characterize that, when we develop our motion cone, we can have a metric for uncertainty in that motion cone, which will actually be useful for safety considerations for in-hand manipulation. So here I've taken a picture from Alberto Rodriguez's group for motion cones, but we're focused more on in-hand manipulation, but our wrench cones will actually look very similar to these motion cones when we actually manipulate objects in hand, and they'll benefit from the continuous representation as well as the uncertainty for in-hand planning. So moving on to intelligence for these types of systems, right? Particularly when you want to think about the case of robots predicting behavior or actions of their collaborators, which could be a human. This is a great breakdown from Marco Pavonia's group here at Stanford that really looks at different ways in which you could think about modeling the trajectory or forecasting the trajectory of another agent. So on the ontological side, you're thinking maybe there's some underlying core structure which you can leverage, like a state space model or an internal cost function. But sometimes you don't have that to really rely on, and particularly when you're predicting behavior, that can be pretty difficult if the game of the task doesn't have rules that confine behavior really well. On the other side, you have these phenomenon-based methods, which are data-driven. These you can imagine as being deterministic regressors or generative approaches. We lean to the generative approaches just because you get this, it's possible to get this notion of uncertainty, which is really important if you want to think about safety further down the line. And then finally, considering the tools that we have, you can think about in past work, how they actually reach consensus in the team is usually through sharing some information, either coming from a base station like an oracle, or coming up with their own thoughts independently, and then using some sort of voting method, information averaging, to reach consensus on what actions should be done. But traditionally, a lot of these implementations are conditioned on the availability of digital communication, which is when you have a human in the loop, this can quickly break down. So transitioning there, what must we consider for human-robot teams? So I would postulate that the key challenge for human-robot teams is that digital communication is unavailable. And so what do robots need to be effective to work with humans? I would say the ability to model complex tasks, the ability to interpret and manipulate environments traditionally configured for humans, and finally, the ability to model teammates' actions and roles. So at this point, I'm going to give some examples of work that we've been doing or working towards in the past year and a half, particularly in the space of wearable robots. So these are ones that perform human augmentation, and external collaborators. You can think of this as a human partner. And under wearables, we break this further down into ability substituting devices and ability enhancing devices. So starting with the ability substituting devices, here you have this common control loop that thinks about how our models how a human might perform a task. There's cognition, which includes planning and control. There's motion or actuation of the body, so having some body dynamics, and then there's some feedback, the sensory feedback you see here from the person. So a key question we have to ask is, if we introduce a wearable, what part of the human is being augmented or substituted? And is the robot augmentation functionally adequate? Does the presence of the robot feel natural or easy to use? So one problem that we're doing that directly addresses this is an intelligent prosthetic arm. So if you look traditionally at these sort of systems, particularly for those who have had shoulder dysarticulation, it's very difficult for them to get back the same level of dexterity in their hands that they once had. And a lot of media, if you look at movies, basically point toward what we like to see, which is an arm that gives them back that full capability. So how can we bridge this in hopefully a as non-invasive way as possible? I'd like to keep wires out of the person, personally. How can we do that successfully? So our approach is to essentially allow the robot to have situational awareness. So the robot is able to observe the task and observe limited input from the human. And that input could come through direct perception action, possibly through an EMG or electromyography, which is a surface mounted sensor that can measure the firing of muscles. And then basically breaking the line of sight for the person with a mixed reality sort of headset. So we hope that these will ultimately become smaller as their uses become wider, but you can imagine understanding where a person is looking and then even augmenting what they're looking at with labels and information that makes it easy to communicate with the human counterpart. And so I place these here in this sort of architecture that we saw earlier. So to get a better idea of how that substituting might occur, this is work being done, by the way, by Shivani Guttasarma and Gabriella within my lab. We have, when humans are controlling this, cognition, right? They're planning, they're controlling. Some EMG signal is being sent to the person's muscles, which are their actuators, and this is causing the body dynamics to move. And then based on how they're interacting with the environment, there's some sensory feedback, what they touch, what they see. If you think about robotic control, we have a lot of these tools ourselves. We have through computing, the planning and controlling ability, we have actuators, we have robotic dynamics, we have a body, we have the ability to sense touch, and we have a lot in the space of vision. So thinking about how this augmentation might occur, you can consider an able-bodied person here, as I just showed on the previous slide. If you have a powered prosthesis, then the person is sending some EMG signal that is causing the arm, in this case, upper limb prosthesis, to move. You could imagine endowing such a prosthetic with some baseline sensory feedback, some vision, some touch. And if you didn't add any additional intelligence, you might be able to have a baseline response, like a basic reflex. If I touch something and it's too hot, then you should withdraw from that so that there's not an accident. And then you can imagine the intelligent powered prosthesis, where all of this information is going into a planner that queries the person, understands the environment, and knows how it should react in order to help the person complete the task. So one of the key modalities here that I think really empower this sort of thinking is this augmented reality breakthrough, which essentially not only allows you to track the gaze of the person, but also to, in a very clever way, use the latest advances in computer vision to augment their environment in an intelligent way and understand what it is they're trying to do, to really ascertain and pull out their underlying intent. And so if we think of this in the scenario of a simple activity of daily living, or an ADL, such as feeding yourself, you could imagine having this state machine. But how would you transition between the different states? This might be governed, for instance, through the limited inputs that the person has. So here, the circle with the plus is where the person's center of gaze is. And then the lines you see here are potential paths that the arm could take. And so in the starting scenario, you could imagine just starting to feed yourself, or if you wanted to have a drink, you would possibly pour from the pitcher to the cup. So if the gaze was pouring, looking at the cup, at the pitcher, then you knew what you wanted to grasp. But then because the affordance of this pitcher is limited, you don't necessarily need the gaze anymore to tell you that you want to pour. It might suffice to take some limited input from an EMG to say, this is the process that I want to do, which is fill the cup and then replace the pitcher. Once that's been completed, then you may want to transition either to drinking or eating, and then gaze in this instance might be useful again if you want to transition to eating. And then if you use existing algorithms on where you would want to actually put the fork to feed yourself, gaze is no longer as important in completing this task for the person. So if we wanted to mathematically state this, we can define a few variables first. So we have the state of our system, which may include the arm and environment. We have the person's gaze vector, we have the person's EMG, and we have the action that the robot needs to take on behalf of the person. And then if this is a finite set, you have a probability of taking a particular action and the sum of that equaling 1. And so being able to predict the wearer's intent can really be stated as this sort of problem. What is the action the human wants to take based on the scenario of the system, which is captured in the state? I have a little typo here. E, which is the EMG signal, and G, which is the gaze of the person. And so by modeling the human's behavior, you can say what EMG signal and what gaze would you expect a person to give, provided the scenario, the state of the system, and the desired action that the person may want to take. And then what are the actions that you would expect to take given the scenario? And so we can formulate this in Bayes' rule and think of this in sort of a Bayesian network paradigm, where if we understand each one of these parameters being either coming from the human behavioral model or the human intent model, we can then use those to predict the overall intent, what action we expect the person wants to take given their limited inputs and the state of the environment. And then finally take that action on behalf of the person. So showing again what this might look like in the case of the intelligent prosthetic, You might have object recognition. It sees the picture, it sees the cup. It realizes the cup is empty, and so task understanding says the likely thing is to pour fluid from the pitcher to the cup. By observing the person's gaze, and let's say in this case, taking the intersection with the table, you can then use that as another indicator of probability about which thing the human wants to actually manipulate. And then given their firing from their EMG, which you see here on the lowest EMG simulated here, what actions would they want to take? How do they want to move toward that objective? And if you combine these probabilities together, this can inform you that the person may want to reach, for instance, for the pitcher. And so thinking about how you might actually generate this data, leverage this data in a very high-level traditional form. Again, if we go to a sort of generative approach, one being the CVAE, you can imagine on the left-hand side here, taking some input data from the person, having some output Y that you want to predict, and then learning to train this latent space vector, which essentially may encode the strategy of the person that is used to actually complete that particular task. And so here are the first steps here in actually solving for those terms. So what does the person want to do given some input? You can expand this and then use the elbow to then solve for what this term actually is. And then we can apply this for the models that we need to learn. So what is the action given the state? This is conditioned on the task. And what is the input from the human given the state and a particular desired action as well? What's really nice, we realized about this framework is that we can actually separate these things into two components. One is having a task-based understanding. So if you have able-bodied persons performing different scenarios, they can generate this huge data set which says, given this scenario, this is the action that you can expect the person to take. And then on the separate side, you can have training of the intelligent prosthesis, which is already done. And so if you tell them what the scenario is and what action you'd like them to take, then you can see what their E and G input would be to achieve that and calibrate the system and then combine those things together to make the system effective for them. So the very first step toward this for us was to actually give ourselves a break in terms of the action and state pair. So we realized if you were playing a game, for instance, you could pull out those probabilities. What's the probability of A moving a particular piece, for instance, or moving towards a piece, given the state of the system or the state of the game. And so here you see these scenarios ranked out in sort of a despot-like fashion that then you can take the probabilities of taking a particular gameplay for your scenario and then understanding what those probabilities would be and associating that as we mentioned before. And so ultimately our goal would then be to then move this to more complex ADLs, such as feeding oneself, putting this in the loop and making this system more intelligent. And our hypothesis is that two things will occur by having this intelligent prosthetic. One, the overall task performance will increase. So here you can imagine before there may have been things that were just impossible to do at steady state, even if given a long time to train. We expect that to increase. And given the ability to understand intent better, we also have the hypothesis that the learning rate will be faster. You'll be able to reach that peak performance quicker. So thinking about ability enhancing devices, these are ones that usually improve some sort of sensory feedback concerning the world. So the first example I'd like to put under this category is our fall prediction and prevention sensor. So ultimately, our goal was to build a sensor that you could put on the person's waist or torso, and that feedback would be useful for a lower limb exoskeleton. In the limit, when you're moving really quickly, a lot of the existing methods try to sample what the person's input is, either through surface sensors or trying to get that signal as soon as it comes from the brain to the muscle. But if you're moving really quickly, let's say you're skipping from rock to rock, as your inertia becomes higher, the time that it takes to go from the brain to the muscle may just simply not be enough. So what is the human doing, right? The human's actually planning. If they are skipping across rocks, they know which rocks they're going to hit, and they know what muscle firings they need to do when they get there. And so ultimately, our robotic systems need to do the same. They need to be able to observe the environment and predict actions that make sense, and that will help them in these sort of time scales. We realized that while that was the long-term objective, there was an easier short-term objective, which is actually having a passive sensor that a person could wear, particularly older adults who are prone to falling, that could actually observe the environment and predict high-risk situations and send them a vibrotactile response in order to avoid that fall. And so the objective here is to take the history of the person's walking through VIO, visual inertial odometry, and then given the observations of the environment, predict over the particular paths, the probability of taking a particular path, the gait over that particular path, and the orientation of their torso, which is correlated to their stability over that path. And so our first goal was to pre-process that data, obtain the VIO information, obtain information about the environment, and then leverage that in a model that's able to then roll out a prediction of the future. And particularly for the stability vector, which is kind of crucial here, this is a term that, that varies even in that field of how do you actually predict stability. But one way that's pretty prevalent is actually by looking at the variance of the person's torso orientation. So instead of just saying, are you oriented with the vertical, or how much angle are you from the vertical, because that can vary from person to person. If you observe the variance in their orientation vector and how that changes, this can be a baseline that works across different people and gait types. In the other space of ability enhancing devices, this was a summer project we did last year with an internship with our RAT teacher, research experience for teachers here, and we expanded this into what we hope to be a paper pretty soon, which is how can we actually enable a mobile phone to perform ASL, American Sign Language translation, that leverages expression detection as well as gesture detection. A lot of methods really look for a single instance, like here you see in the bottom corner, understanding the pose of the hand. But just like any other language, the sequence actually matters a lot. And so we have proposed a platform that's very similar to some of the leading works in CAMGAS and how we can actually use a transformer to extract that sequence of language and understand what's being said meaningfully. And the goal being to basically leverage intelligent feature gathering in a sort of modular network manner to then understand how we can actually miniaturize all of this for mobile deployment. So moving to external collaborators, one of our projects in this space, which is one that was a continuation from some work I did in my PhD, was how you can have a human-robot team for cooperative transport. And so if you watch how people work together, they're able to carry objects in cluttered environments with limited communication. And the communication they do have that's prevalent is the forces in the object that they're transporting. And so our question was, can we observe how humans work together and carry, and then transfer that ability to a robotic teammate? So here in this instance, you have knowledge of the input from the other person, the observations of the environment, and you're trying to basically model their latent strategy. What is their strategy for getting through this environment? So COVID struck, and we realized that this was a perfect opportunity to get our simulation game on track. And so we built this online simulator that allows multiple people to log in and essentially apply forces to the system to travel through waypoints, measuring forces in collaboration as they do so. And here you can see an indicator even for the interaction forces inside of the object being transported. And so with this, in our virtual environment, we wanted to observe how humans work together. So what's their underlying policy? What actions do they take given states and observations? Understand and transfer that ability to a robot, essentially using a latent strategy, Z sub H. And then transpose this to a real system. How do humans do this on real platforms, physical platforms? And then how can we actually allow our robot to effectively work with a human collaborator in that instance? Another case for an external robotic collaborator is a system that would work with a person to complete a complex task. So this problem has two components. One, if you want to do a complex task, how do you effectively describe it to the robot? So in these instances, the leading approaches are those that are found in inverse reinforcement learning, or learning from demonstration. And those can be very expensive when it comes to the data you need to actually tell the robot how to complete this task. But if you could actually leverage some fundamental knowledge of your system, such as these are the rigid bodies you're going to interact with, these are the constraints that you're going to interact with, and these are the sequence in which you're going to interact with them, then you can actually increase the rate at which your system is able to actually learn the fundamentals of that problem. And then through state space reduction. And then on the other side, if you're completing a task with a robot, such as carrying boxes from one location to another, if the robot realizes that the human is suboptimal, but it understands what the overall task is, the robot may be able to model the human's behavior and understand what the robot, needs to do to make the overall team more effective. Simple example, if you have heavier and lighter boxes, and if the human carries heavier boxes, it'll take the overall team longer to complete the task. Then by observing the human over time, the robot can understand that their strategy is to move heavier boxes, which is suboptimal for the overall team. And so then the robot would then pick up the heavier boxes, which is arguably easier for the robot, forcing the human to carry lighter boxes, which would make the overall team efficiency increase. The last project I want to talk about here is our embarking into the self-driving autonomous vehicle space. And the sort of thought that we have here is, when we think about self-driving vehicles, usually we think of it in terms of giving control completely over to the robot. That's it. Let's remove the steering wheel. That's it. But I would argue a lot of people are probably very interested in being able to have some control at some point, which I'll show in a few slides, relate to levels of autonomy 3 and 4. And so in this case, the question is, how can the vehicle facilitate both safe and smooth transition of control between the vehicle and the driver? So if we go back to our problem that we saw before here, the robot is your intelligent vehicle, your environment is what it observes, and your driver is the human collaborator. Again, motivating this sort of parallel versus shared autonomy. Having a self-driving car is great, but there might be an instance when you might want to take over. So how can we do that in a safe way? So if we think about the levels of autonomy, 3 and 4 really lend themselves to collaborative robotics, right? This conditional automation. The human driver may be able to take over in certain modalities. So what are the risks from arbitrarily taking control from the human? One question you have to ask is, does the vehicle have an accurate model of the plant dynamics? And the risks for giving control back to the human, does the human have an accurate internal model of the plant dynamics and an effective control strategy? So we're going to focus on this second question. And how do we determine this? Through human intent estimation and action prediction. So consider this scenario, right, where the vehicle is in control, and at time T sub S, you want to switch control from the vehicle to the driver. Right? If you do that, just sort of cold turkey at T sub S, a few things might happen. The human might stay in their lane, which is a safe set, or they might actually leave the safe set, as you see here with the red indicator, or leaving the green box in the top right corner. However, if you have the ability to model the behavior of the human and take some input from them over a period of time, you could determine if their actions or their strategy remained in a safe set. And if it did, you could actually bound that region, and this would tell you that you can actually safely hand over control with a high % degree of trust that the person will remain in that safe set. And so here is a template sort of control diagram you could imagine where you're modeling the human's action model, you have the underlying dynamics of the vehicle, and then you have the robot's action policy, which understands either the actions of the human, predicts them, or uses a latent strategy to do so. And based on that information, can have blended control when transitioning control back from the robot to the human. So with that, a few takeaways I'd like to leave you with is to be an effective collaborator with humans. Robots must be able to model humans' behavior and their role. There's significant room for improvement in robotic hardware for alternative forms of communication, such as audio, visual, or tactile. And robot collaborators have the potential to expand their human teammates' capabilities, therefore enhancing and restoring their quality of life. Thank you very much.
Okay, thank you for a great talk, Monroe. I'd like to now open the floor to questions. Everybody feel free to unmute yourself and ask any questions you have for Monroe.
I'll go ahead and start off with something. So you showed at the beginning these basketball players on a team where they've like heavily practiced with each other, right? Not necessarily other basketball players, but that specific team. And then you showed this kind of Bayesian classifier with these priors. And I'm curious where the balance is of classifiers that come from a population versus a team versus an individual collaborator, and how you affect that.
Yeah, so that's a great question, right? And so just rephrasing it, make sure I'm on track. So if you think about like, how the human agents are, in this case, like for the basketball scenario, how they work together, absolutely, right? They had a chance to work with each other. And I would argue, right, they understood each other's strategies, right? What they were able to do, what they were capable of doing, and obviously agreement on the objective. So they learned how to play the game, they knew the objective, and then they understood each other's capabilities, right, to actually achieve that. So, in the Bayesian framework I mentioned was only one of quite a few approaches to do this. But across the board, I would say this sort of generative modeling is really important, right? So if you understand what the task is, and that's really important, that we're fundamentally putting this behavioral modeling in the context of a task, right? Can you understand your neighbor's strategy? And that, as you said, quite astutely, comes through observation. You have to understand what they're capable of doing. Maybe this can be given to you in some sort of prior, but if it's data driven, this comes through observation, this comes through interaction. And once you have it, then you can understand that mutual strategy on how these agents might in fact work together. So, going back to that Bayesian note that you mentioned here, right? The actions that each other take, right, might be conditioned on what you're trying to do, the task, but also there's this sort of mutual conditioning between the agents on each other, this sort of closed loop that's cycling. And this is formally known as like the theory of mind, right? I know what you're thinking, that you're thinking about me, that I'm thinking about you, and we go forward like this, right? And you have to have this understanding about how they're going to react. What's their policy based on that, and understand the role that your actions may take in informing the agent's interaction. But yeah, long story short, generative approaches, I think, are the best way to begin to address that.
Yeah, if I can dig a little bit deeper on that, like a specific example, right? Let's say that I'm cooking with my wife, right? Like I know my wife so well that I can understand what she's about to do. But if you and I start trying to cook, like I know you are human, I know you've got some basic skills, maybe with a knife or whatever, but I don't really know how you move. And so how do you blend and start off with maybe that general knowledge of people and then go specific to the individual you're collaborating with?
Yeah. So this is a great point. And I'm going to point you back to the latent strategy. So let's say for all people who are, knowing how to cook, or in this case, like cook in this example, that you can basically manipulate objects in your kitchen. I know how to pick up a pan and do all of this, right? So there's this fundamental low dimensional strategy, right, that is present with some statistics. I'm going to pick up this pan, right? I can pick it up, but there may be some slight variance in how I actually achieve that, right? And then, that's a baseline model prior you can apply to anyone you're going to interact with. That's being human, knowing how to do basic things. But then maybe when you cook, right, there's this dance around the kitchen that you rotate in a circle such that you're never in each other's way, right? And so the strategy is going to need to move in order to meet that. And so this is an active area of research that we're looking at. We have interest at Berkeley too, on how you can actually have latent strategies that are able to update with your partner as you continue to interact. And so you could think of these as mobile latent spaces that are moving through interaction.
Very cool. Very cool.
I have a question about collaboration. Thank you for your talk. It was great. Yeah, I was just kind of wondering what you thought the role of facial expression is in these sort of collaborative spaces. Like you had that simulator where humans can collaborate carrying rectangles around. Do you think that that would have the same sort of strategy as if you have two, let's say, normal or average humans collaborating, carrying something or working together?
That's a great question. And so one that we've been thinking about, and even a little bit concerned with when it comes to translating to the simulated environment. Originally we were thinking that facial expressions might play some role, and you could collect that data as agents work together, as humans work together to transport an object from one location to another. So it could play a role. I can't say right now what that role would be and how important that role would be compared to, let's say, tactile information that comes from actually communicating through forces, which are even more prevalent and even seen beyond even humans, even in ants, right, as they carry objects together. So that's the short answer for the carrying case. But in general, I think, these modalities, it can be another source of intent measurement. Right? If you were to even classify very basic things like a frown or a smile as being okay with how things are going, or wishing that things were different, that could be useful. Particularly in my work, the only one that really focuses heavily right now on facial expression is the ASL case, because we realized that, and even we've gotten feedback, high-level feedback from the community, that if you have these facial expressions, this can actually give context to some of the communication that's being performed. And so it's very important in that scenario. So across the board, it's unclear, and this could even be, between different cultures, things might be different. But at the very high level, at least, we do know that it's an important thing to consider and keep in your bag if it's possible to collect. Yeah.
Hi, Monroe. I really enjoyed your talk. I just love the sort of frame of reference that you bring to things. I was curious, with the multi-agent coordination, you talked about different strategies, but then you mentioned, like, once you throw the human in the loop, these sort of, either don't work or fall apart. I was wondering if you could just more speak to that issue and how this, I guess, I'm curious how your general approach kind of fits into that challenge.
Yeah. So that's a great question. So a lot of our talks, or a lot of the projects that I mentioned so far, really sort of had dyadic teams, right? There was either the prosthetic in the person, or the robot carrying across from you, or the vehicle in the person. So none of the current projects we have scale up to multiple agents. And so I'm going to brainstorm with you now how we would think about that, as they haven't been currently addressed in the baseline projects that we have. So in the methods that I had spoke about, right, for robotic agents, there was this digital communication tool that is just the primary assumption when you have robots working with each other. They're able to communicate possibly with a limited radius, share key information in order to meet an overall objective or strategy. When you bring a human into the loop, right, that whole modality, of digital communication usually breaks down pretty quick. But as I mentioned, you still have that vision, auditory, or tactile information that you can still pull from. And so the question that comes back is, can they actually share that mutual information through these other modalities? And I think nature provides a great example, or many examples, by the way, when that's actually possible. So I think, in future slides, I'll be sure to include this. But if you think about the Intel drones flying in unison, and then you look at a flock of birds, how did they achieve that, right? And there's no digital communication happening with a flock of birds, either in V formation or even just, flying as a swarm. They're not colliding, and yet they're moving as quick or even quicker in some cases with harder dynamics, right, than the quadrotors. How? Right? So clearly, right, if I'm in this swarm of birds, if I think about a first person view, which actually would be a really cool paper. I think Costas was doing something with birds a while ago. If you could actually put a headset on the bird and see what they saw, they probably can't see the entire population of birds that are in the air, probably only the local agents. And there are probably local gradients that they're trying to maintain. They're trying to maintain a distance from all nearby agents for protection and both, to not collide as well as to just move in unison, right? And so there's this sort of visual, possibly auditory feedback that helps them all to understand how to interact, which means they all have to, again, if we go back to our trust model, have a shared objective. We don't collide because that's bad. And then we all have to know what each other can do. If the birds' dynamics were so bad that they were not able to change direction quickly, then you need to spread out. The minimum distance of the swarm needs to increase to allow for the control authority of every agent in that swarm, right? And so by having this information, this gives you the framework on how this swarm could work together using whatever feedback inputs, communication modalities they have. Does that answer your question?
Yeah, well, I think it was just sort of, I was thinking like, it also depends, using your sort of bird analogy, like, if the environment changes, then all of a sudden, like, the shared understanding of how that should affect group behavior is also something that's only learned through sort of being a member of that community. Yeah, I just think it's interesting. Yeah, I thought that you kind of identified that challenge as like I was like, yeah, that really is, because also there's teams within teams. Like we can iterate on this continuously and how information gets shared. And then when you think of sort of using the basketball example, or just, like a scientific team, how humans coordinate is it's so not just hierarchical, like that, try to think about that as a model for how agents and humans should interact. I thought that was interesting.
Absolutely.
Okay, thank you very much, Monroe. I think it's 4 o'clock, so we don't want to take up any more of your time. And thank you for this great talk.
My pleasure.
Thanks, Monroe.